Hello, everyone, and thank you for coming. My name is Brian Milano, and this is my partner, Trevor Straub. Today, we'll be discussing our cooling system design for the IGCT module. For this project, we were tasked with designing a heatsink that could handle the continuous loss of 500 watts while maintaining an operating temperature of 125 degrees Celsius. In order to do this, we made it our goal to calculate the optimal size, type, and quantity of fins in a heatsink with our own custom parameters to ensure proper functionality while maximizing efficiency of materials and cost. In order to make a successful design, we first had to understand what a thyristor is. For this application, a thyristor is a power semiconductor electronic device that is used as a switch for electrical current in an industrial equipment. It is made with the integration of a gate unit with the gate commutated thyristor or GCT wafer device, allowing for fast communication between the current from the cathode and the gate. The benefits of using a thyristor is its small size, low heat loss, low production cost, its high switching frequency, and its ability to handle high voltage applications. We decided to go with a flat fin design instead of a pin fin design. We chose a flat fin due to its increased surface area and stronger design, especially when paired with a uniform air convection. As shown here, the base and the fins are both made of copper and are attached to the thyristor. The fin parameters we set were 0.3 millimeters thick with the width of the base being 60.09 millimeters and the length of 20 millimeters. We chose copper because it has a high thermal conductivity and is relatively cheap and easy to come across material. That being said, copper also has a high resistance to erosion, making it very durable. For this design, we made multiple assumptions based off the information given to us. We assumed that the system was steady state and one-dimensional. There was negligible contact resistance, heat transfer through the sides of the resistor, and negligible radiation. Due to the design of the system, we also assumed that there was uniform convection airflow through the channels, the cooling was double-sided, and that the fin tips were adiabatic. By making these assumptions, we were able to simplify the conservation equation and the heat diffusion equation to better suit our needs. Also, since we chose copper for the material of the system, we assumed the thermal conductivity of copper to be 401 watts per meter Kelvin. After assuming steady state and one-dimensional heat transfer and neglecting the contact resistance and any heat resistance, we were able to finalize our thermal resistance model as shown here. Because the resistances were all in a direct sequential contact with one another, the thermal resistance model is best represented by a series circuit where resistances will be added. We neglected the contact resistance between the base and the thyristor because the value obtained was so small that it had very little to no effect on the overall performance of the heatsink.
When creating our design, we chose predetermined values for the characteristics of the fins. This allowed us to focus on solving for the number of fins required to ensure that the system functioned properly under the max operating temperature. We first solved for as many resistances as we could to use later in the solving process. Next, we decided to calculate for NF so that we could use that value in our equation to solve for N naught. After calculating both of these values, we finally had the information we needed to solve for the final resistance. To do this, we used the thermal resistance equation using temperature variation between the source and the ambient temperature, and the work above shows how we were able to find the final resistance needed before moving on to the fin equations, where we could be able to solve for the number of fins algebraically and then in the end graphically. After all the necessary values were calculated, we used those values to solve for the total number of fins needed to ensure that the system operated successfully. After arriving at the equation at the bottom of the sheet, we used a graphing method to solve. Since this is a two-sided cooling system, 68 of the 136 fins calculated would be found at the bottom of the thyristor. This value makes sense for the size and surface area of the heatsink, because the fins are 0.3 millimeters thick, and the space between the fins is approximately 0.58 millimeters wide. This ensures a relatively even distribution of fins across the entirety of the system. It also allows for many contact points to oppose any force of 40 kilonewtons which might be applied. We were then able to use the lump capacitance method to determine that our heatsink would in fact be successful in allowing the system to operate at twice the thermal load. We determined that if the heatsink had 136 fins, it would take approximately 11.8 seconds for our heatsink to go over the max operating temperature, set at 125 degrees Celsius. However, the system was to run at 1000 watts for 10 seconds. If it was to do this, the heatsink would be vital in maintaining an operating temperature and would succeed in doing so. In the end, our design worked properly and completed the requirements for the task. We were able to determine the total fins required, which was 136, and we were able to prove that the design could in fact remain viable for at least 10 seconds during the overload. If we were to come across this problem again, we might have tried to make the fins longer, or even change up the material to see how it affected our results. Our choice to use a square base and fins rather than a circular base and pins was beneficial to the overall simplicity of the design and made for a simple yet powerful heatsink. And here we just have the final list of contributions for further reference. Thank you.